In the relational model of databases, a candidate key of a relation is a minimal superkey for that relation. That is, a set of attributes such that the relation does not have two distinct tuples with the same values for these attributes. There is no proper subset of these attributes for which holds. The constituent attributes are called prime attributes. Conversely, an attribute that does not occur in any candidate key is called a non-prime attribute. Since a relation contains no duplicate tuples, the set of all its attributes is a superkey if null values are not used. It follows that every relation will have at least one candidate key. The candidate keys of a relation tell us all the possible ways we can identify its tuples. As such, they are an important concept for the design of database schema. Example: the definition of candidate keys can be illustrated with the following example. Consider a relation variable A with attributes that has only the following two legal values A1 and A2. Here A2 differs from A1 only in the A and E values of the last tuple. For A1 the following sets have the uniqueness property, that is, there are no two distinct tuples in the instance with the same values for the attributes in the set, A, B, A, C, B, C, A, B, C, A, B, D, A, C, D, B, C, D, A, B, C, D. For A2 the uniqueness property holds for the following sets: B, C, B, D, C, D, A, B, C, A, B, D, A, C, D, B, C, D, A, B, C, D. Since superkeys of a relva are those sets of attributes that have the uniqueness property for all legal values of that relva, and because we assume that A1 and A2 are all the legal values that A can take, we can determine the set of superkeys of R by taking the intersection of the two lists, B, C, A, B, C, A, B, D, A, C, D, B, C, D, A, B, C, D. Finally we need to select those sets for which there is no proper subset in the list, which are in this case, B, C, A, B, D, A, C, D. These are indeed the candidate keys of relva R. We have to consider all the relations that might be assigned to a relva to determine whether a certain set of attributes is a candidate key. For example, if we had considered only A1, then we would have concluded that A, B is a candidate key, which is incorrect. However, we might be able to conclude from such a relation that a certain set is not a candidate key, because that set does not have the uniqueness property. Note that the existence of a proper subset of a set that has the uniqueness property cannot in general be used as evidence that the superset is not a candidate key. In particular, note that in the case of an empty relation, every subset of the heading has the uniqueness property, including the empty set. Determining candidate keys. The set of all candidate keys can be computed, for example, from the set of functional dependencies. To this end we need to define the attribute closure for an attribute set. The set contains all attributes that are functionally implied by. It is quite simple to find a single candidate key. We start with a set of attributes and try to remove successively each attribute. If after removing an attribute the attribute closure stays the same, then this attribute is not necessary and we can remove it permanently. We call the result. If is the set of all attributes, then is a candidate key. Actually we can detect every candidate key with this procedure by simply trying every possible order of removing attributes. However, there are much more permutations of attributes than subsets. That is, many attribute orders will lead to the same candidate key. There is a fundamental difficulty for efficient algorithms for candidate key computation. Certain sets of functional dependencies lead to exponentially many candidate keys. Consider the functional dependencies which yields candidate keys. That is, the best we can expect is an algorithm that is efficient with respect to the number of candidate keys. The following algorithm actually runs in polynomial time in the number of candidate keys and functional dependencies. K, 0, equals minimize, A. /A is the set of all attributes /n, equals 1. /number of keys known so far /I, equals 0. /currently processed keys while I, n do, for each I plus or minus ai squared f do, s, equals I plus or minus a. Found, equals false. For j, equals 0 to n1 do, if k, j, s then found, equals true. If not found then, k, n, equals minimize, s, n, equals n plus 1. The idea behind the algorithm is that given a candidate key and a functional dependency, the reverse application of the functional dependency yields the set, which is a key too. It may however be covered by other already known candidate keys. If not, then minimizing the new key yields a new candidate key. The key insight is that all candidate keys can be created this way. See also, alternate key, compound key, database normalization, primary key, relational database, superkey. Prime implicant is the corresponding notion of a candidate key in Boolean logic. References. Date, Christopher. 5. Integrity. An Introduction to Database Systems. Addison Wesley PPA 268-276. ISBN A978-0-321-18956-1. External links, Relational Database Management Systems, Database Design, Terms of Reference, Keys, an overview of the different types of keys in the RDBMS.